Hey, welcome back to Fat Mama Physics. This is another video on 2D momentum problems. I will do example 3, which is this one. You get to do the next problem, which is example 4. Of course, you're welcome to try example 3 as well. But let's get started right away. We have a 4 kilogram bowling ball. I'm going to call this mass MB. Like MBA? Okay. No, that's NBA, sorry. Is moving east at an unknown velocity. Ooh, unknown velocity. I'm going to call that U because that's before something happens. It will collide with a 6.1 kilogram frozen cantaloupe, which I'm going to label MC, like the person MCing concert. Okay, it's at rest. Oh, hey, this one's at rest. We like at rest. Sorry, so that's UB. And this is going to be initial velocity of the cantaloupe at the beginning, but it's a 0 meters per second. We love 0 meters per second. After the collision, the bowling ball is traveling at a velocity of 2.8 meters per second, 32 degrees north of east. Okay, so this problem, we start off with some directions here. This, I'm going to label V for final velocity. After the collision, VB for the bowling ball. The cantaloupe is traveling at a velocity of 1.5 meters per second, 41 degrees south of east. So that's the velocity of the cantaloupe. What was the initial velocity of the bowling ball? That's UB. So that's what we are going to solve for. First thing we got to do is we are going to draw a picture before and after the collision. Okay, so here I have the beginning picture where the bowling ball is going to crash into this frozen cantaloupe. It's at rest, which is good. And then after the collision, what I'm drawing here is this bowling ball is going to move north of east. So that's some diagonal direction that's that's in the northeast quadrant. And the directions is 32 degrees north of east. So to decipher this, we're going to start from here at where we start off with. And remember, this direction here is flipped. So we go east first, and then we go north. So this angle is this one here. I'm going to draw a line, and my angle is 32 degrees right there. This velocity here is 28 meters per second. Now for the cantaloupe, okay, the cantaloupe is going to go off, snug and tight together, some sort of southeast quadrant, so somewhere in this direction. And then the 41 degrees is south of east, right here. Now, because this is flipped, these two directions are flipped, we go east and then south. So starting from the beginning, the starting point, I'm going to go east, and then I go south. So this angle here is 41 degrees. And that's how we decipher the degrees, the angle. The cantaloupe is going at, final velocity of cantaloupe is 1.5 meters per second. Okay, so we want to find out in this problem what UB is. That is the initial velocity of the bowling ball. Okay, so it's time to write our equations. Before that, I'm just going to say that going towards the east is going to be positive. Going up is going to be positive. Important to state your directions because your positives and negatives will matter when dealing with these problems. Let's start off with the x direction. First of all, we have the bowling ball going just east. Okay, so that's positive. So that's mass of bowling ball times its unknown velocity in the very beginning. The cantaloupe has 0 momentum, so we don't even put that in anywhere. After the collision, the bowling ball is going off at a diagonal in which part of that, a component of that, is going in the x direction, so the positive eastward direction. So we need to account for that. With our right triangle being this x component is going to be adjacent to that angle. And that's MB times its final velocity times cosine of 32 degrees, being adjacent. Same thing with the cantaloupe. Cantaloupe is also going off at a diagonal, meaning it will have a horizontal x component. And we need to add this one because it's also going east. So that's mass of our cantaloupe times its final velocity. This side of our right triangle here is also adjacent to this 41 degrees. So that is also cosine of 41. Okay, so that's our first equation. I'm going to use red for the y direction here. And you will notice that at the very beginning, before the crash, there is no y component momenta, okay? So that is, in fact, 0. We can just write 0 in the equation. That is equal to, now, we have one vertical component from the bowling ball, which is this guy over here, and it is opposite to our 32-degree angle, so that's going to be MBVB for final velocity of our bowling ball times sine, because it's opposite to the angle, and that's going to be positive because it is north. We said north is going to be positive. On the other hand, this cantaloupe is moving some direction southward, in which we will need to subtract this momentum because it is going in the opposite direction to north. So that's subtracting mass of the cantaloupe, velocity of the cantaloupe, and this vertical component here is it's opposite to the 41 degrees, so that's going to be also sine of 41 degrees. Now you might be thinking, can I just say these two momentum are equal because they should be equal to one another because they sum up to 0? You are correct. In fact, if I do move MCVC sine 41 to the other side, it gives us directly that. So that turns into MCVC sine 41 equals to MBVB sine 32. So yes, you're absolutely right. They are equal. But in fact, we don't even care about that. We only want to find out the initial velocity of the bowling ball. So that's UB. And we need to check if we know everything else in this equation. We have mass of the bowling ball, final velocity of the bowling ball, we have cosine 32, mass of the cantaloupe, final velocity of the cantaloupe. We have everything. We, in fact, just need that first equation. Lucky us, we don't even need the second equation. Okay, so take that down here. We solve for UB by dividing both sides of the equation by MB, mass of the bowling ball. Mass of the bowling ball here cancels. We get UB is equal to MBVB cosine 32 plus MCVC cosine 41 all over MB. Now putting in all our numbers, mass of the bowling ball was 4 kilograms, and its final velocity was 28 meters per second. The mass of the cantaloupe was 6.1 kilograms. Its final velocity is 1.5 meters per second. And then the rest is just stuff we know. Okay, we put all of this into our trusty calculator, and we are going to get 4.1. Don't forget bracketing and doing things properly on your calculator. 4.1 meters per second. And you are very lucky because the question tells you it was moving east already. We should state the directions because it is asking for a velocity, which is a vector. So 4.1 meters per second east is going to be our final answer, okay? So in this problem, notice that what's a little bit different was that you can have 0 momenta to begin with in a certain direction, and if they are momenta in those directions after the collision or the event, then we know that all of them would have to sum up to 0, okay? Which probably you will have to apply in this next problem here. Hey, first let's just make sure we understand everything before I let you go and try it out. We have a 650 gram plate. Hey, it's in grams. It is dropped and it will be shattered into 3 pieces perfectly. Like that's never going to happen. Along a plane parallel to the ground. So what that looks like is, let's say I'm looking at the plate on the side view. It's coming down, it's going to hit the ground, and I'm going to have trouble drawing this 3D way, but imagine one piece shatters here, one piece shatters like into the page kind of, and then one shatters here. So essentially, this shattering is along a plane, along a sheet of paper that is parallel to the ground. So that's what it looks like. So if I was looking at this diagram here, then this would be a bird's eye view, me looking at the ground. Okay, so what's happening. So we don't even care about the vertical direction, the direction that's going down to the ground. So that's it's a terrible modeling of the problem in real life, but for the sake of us trying the problem out, we would have to be okay with that. But alas. Okay, so we have a 300-gram piece. It is traveling north at 7 meters per second, and that -1 sign is just per. It's a divide seconds. That's what it means. 150-gram piece right here is moving 34 degrees south of east. Okay, so that's a right triangle right there. At 8 meters per second, calculate the velocity of the last piece. So this guy over here, we don't know anything about that last piece. Okay, so that is your task, is to find the velocity of the last piece. You'll need to apply everything you learned in this video and in the last video to help you out. I wish you good luck. Good time to pause the video. Now I will do the solutions on Fast Play. First, we need to figure out the mass of the last piece, which then we just have to take the total mass of the plate, which is 650 grams, and subtract it by the 300 grams and the 150 grams of the two other pieces, giving us 250 grams of that last piece. Now we can try to figure out the before the plate's shattered. Before the plate shattered, along the plane that is parallel with the ground, there is no momenta. There's only up and down momenta. There is no momenta in the north, south, east, west direction. So we have 0 momenta in x and y. After the explosion, with the plate shattering, we have north being positive, and I chose east being positive for directions. That's after the collision. Sorry, that's after the explosion, the shattering. Making sure we get our masses in kilograms, we can write that before the collision there is no x momenta. After the collision, we have the 150-gram piece traveling the positive eastward direction. The component would be cosine 34 because that's adjacent to that angle. Now we have to subtract the other piece that is going westward. So that's the other piece, cosine theta, which we chose that as is in the diagram because it's adjacent side of that angle. In the y direction, we have 0 to begin with again, and after the shattering, the ups equals the ups minus the downs. So the up is the 7 piece, which is directly north, and the y components of both will both use the sine theta, in which that should be sine 34, which is the one we know. We will need to simplify this because we can combine a few terms together of numbers that we can just calculate here. So we're going to isolate for the term that contains both our unknowns. We're going to put that to the other side, and we're going to calculate the two terms in which we know all the numbers too. And this is going to give us, after we do some calculations, 1.428, etc. Okay, we're going to hopefully save that into a calculator. Units are still in momentum, so kilogram meters per seconds, and that's equal to the other side. Now what we can do is we can take the x equation and isolate also the term with both our unknowns. The purpose is to get the angles on one side, so we can do some sort of elimination. Okay, so then doing that, we move one term to the other side, giving us that equation there, and which we are going to use and divide our y equation by our x equation to get sine theta over cosine theta. So hopefully we'll get be able to put those together and get tan theta, just like we did in some previous problems. So then dividing both sides of the equation just like that cancels out our mass and our velocity there. So that's eliminating a symbol. That way we can have one less unknown to worry about in this equation. So then we can solve for tan theta here, because sine theta over cosine theta is tan theta, as we learned before. And solving for the angle here gives us about 55 degrees. So then we can use this angle and plug it in either the x or the y equation to solve for our velocity. And it doesn't matter which one you plug in, we can just plug into the easier one with less numbers to work with. So that's our x equation there. And we're going to first solve for v first before we plug it in, so less work for us later. And dividing both sides by 0.25, cosine theta, which we know the theta, which is 55 degrees. Putting in all our values in here, cosine of 55 is what we found. That's going to give us a final answer for this velocity of that remaining piece as 6.96. That's going to round to 7 meters per second at 55 degrees. And we're going to use the degrees in the diagram there. That's going to be south of west. Okay, so I applaud you for bearing with this whole problem, going through it, and even watching the solutions together with me here. The biggest thing that I want to talk about the solutions is the fact at the beginning we don't have any momenta in the x and y direction at all. And I kind of glanced over it before we did this problem. The fact that when the plate drops, all of its momenta is along the, is up and down. And when it shatters on the ground, it's kind of going off in a direction that's parallel with the ground. So that's why we have the north, south, east, west directionality, not the up and down direction. So before the plate hits the ground, it does not have any of those components. So that's why there is 0 momenta in the x and y direction to start with, because all of these directions here, they are parallel with the ground, not the up and down direction. You might be thinking, well, does that not mean that then where did all that momenta in the up and down direction go? Shouldn't that be shouldn't that be conserved as well? It is conserved, and it's not part of this question. It takes some outside, and you're not required to know that for this question. But what actually happens is that when this plate crashes on the ground, there is Newton's third law here applies. You have an external force that that causes this plate to stop very much almost instantly due to its reaction with the ground. So there's that upwards external force in the upwards direction that would slow down the plate, but then there's the impact due to it shattering on the ground, in which the momenta along this plane that's parallel with the ground, that momenta there is constant that you can calculate, and that would be conserved. So this plate coming down from the top, crashing some net external force there, that's outside the problem. You don't have to consider it. And I think that might be what is confusing us, because you might be thinking that, okay, shouldn't some of this momenta after the crash be also in the upward and downwards direction? And yes, momenta is always conserved, but in this case, it was the impulse from the ground that caused it to stop, and it's shattering. The shattering portion was the part that you needed to solve in this problem. The up and down that you don't need to even worry at all. So hopefully that explains to you kind of what's happening. If you can solve this problem without any help at all, it's you're absolutely ready to go. It is a tough problem. It's a tough problem. Notice that you have to apply not only what we learned in the last problem with the 0 momenta in the x and y direction, but also you had to substitute in here tan theta equals to sine theta over cosine theta we learned in the last video. And oh, right. And also the fact that I didn't tell you the mass of the remaining plate piece, but hopefully by process of elimination, you know that the plate has a total mass of 650 grams, and you just need to subtract the other pieces of the other plate pieces to get the mass of that final piece there, which is 250 grams, okay? Okay, well then. Thank you for bearing with me through this video, and also to congratulate you for doing and conquering such a difficult problem. I wish you good luck on the rest of your problems, and Fat Mama Physics signing out.